Welcome to another podcast. In this episode, we're going to be taking a look at partial fractions decomposition. So let me go ahead and get the integral up that we're going to be looking at today. I want to take a look at the integral of 2x plus 1 divided by, and I'm going to go ahead and have it in factored form here, x minus 2 and then x minus 3. So obviously, if the denominator is not factored, that should always be your first step. Partial fractions is a technique that allows us to work with rational functions. And so a rational function is any function f of x which is of the form p of x divided by q of x, where p and q are both polynomials. Now, in order to use the methods that we're going to be using, a couple of things need to happen. We need the degree of p of x to be less than the degree of q of x. This is what's called a proper rational function. We borrow that name from proper and improper fractions. As is the case here, notice that on the bottom we have degree 2 polynomial because there's two factors, and on the top it's a linear degree 1. So this fits perfectly for the method that I want to show you, and that method is cover-up. So let's look at the decomposition first, and then we'll break it down further from there. The decomposition is to take the fraction 2x plus 1 over the factors, and imagine that you can rewrite this as a set of partially defined fractions. That's where the name partial fractions comes from. And those partially defined fractions are two fractions having the factors as their denominators with unknown numerators. Now, I still need to maintain this relationship, this proper relationship, even among the partial fractions. So because the factors themselves are linear, I need something that has degree less than linear. Well, the only thing less than linear in degree would be a constant, and that's why I have both a and b on top. Alright, in order to figure out a and b, I'm going to have to use a method called cover-up. Now, you've seen me use this in class, and I've defined it a little bit in terms of the limit. Let me go ahead and further define it here. If I'm wanting to find a, then that's equivalent to finding the limit as x goes to 2 of x minus 2 times the original fraction. Now, in class I use sort of a device to help us do this where I cover up the x minus 2 on both sides, and then we plug in 2 into what remains. But this is the exact same thing mathematically. So if I do this, I see the cancellation occurring here, and then plugging in x equal to 2, I'm going to get 5 on top and what looks like negative 1 on the bottom. So negative 5 is the result for a in that case. And then b is similar, but b, the root is 3, so I'm taking the limit as x goes to 3 in this case of x minus 3, taking that factor times the original fraction. Alright, I get another cancellation to occur here. Plugging 3 into everything that's left, I get 7 on top and 1 on bottom, and so b is 7. The point is that my decomposition now says that I can take the integral of 2x plus 1 over x minus 2, x minus 3, and rewrite this as the integral of the first piece is negative 5 over x minus 2, and the second piece is 7 over x minus 3. Just simply plugging in each of these pieces. So, a is negative 5, that goes here, that's equal to negative 5 now, and b is 7, so that goes here. And I'm just taking that decomposition and writing it in integral form. Alright, if I then try to solve this integral, I can use the properties of integrals, of definite integrals here, to write it in this form, distributing the integral to each piece. And then at this point in the semester, we should be fairly comfortable with saying that this is the natural log of x minus 2, and this is the natural log of x minus 3. And obviously plus a constant. So this is just a short introduction to the cover-up method that we've used in class. It only works in the case where you have linear factors. So these are what we call linear factors. You can't have repeated factors, you can't have quadratic factors. Now we're going to do a couple more examples coming up where we do introduce those, but we'll have to handle them differently. Alright, thank you for watching.